Hello all. Today we are going to discuss about fourth normal form and fifth normal form. So outline of today's lecture is multi-value dependencies and fourth normal form. So we'll be defining multi-value dependencies and fourth normal form, and we'll discuss one example also. And then we'll define joint dependencies and fifth normal form, and we'll see one example. So in simple terms, this fourth normal form is that it should satisfy BCNF. Okay, so which means it should be in BCNF, and a relation should not have more than one multi-valued attributes, and it should not have multi-valued dependency. And multi-valued dependency, what is meant by? So this is just an informal definition. So what is meant by a multi-valued dependency? Suppose we have a dependency like A to B, and we can call it as a multi-value dependency if for a single value of A, for a single value of this A, we can have more than one value, more than one value for B. Then that is known as a multi-value dependency. A to B is a multi-value dependency, and you can denote it like you can have two arrowheads, and you can say that it is a multi-determines. A multi-determines B, which means a relation should have at least three attributes to have multi-value dependency. So when we have a relation with two attributes only, for example, suppose we have attribute A and attribute B, and suppose attribute A has values A1 with, for example, A1 has two values for B, and A1 has values B1 and B2. And for another example, A2 with values B3 and B4. If that is the case, which means a relation has two attributes or two columns, in that case, what will happen? We'll be able to solve this problem, that is the multi-value dependency for this two attributes, by converting that into multiple rows. Okay, that is, for example, we can write it as A1 B1 is one row and A1 B2 is another row, and A2 B3 is one row, then again A2 B4 is another row. Okay, likewise, we can use multiple rows to solve the problem of this multi-value dependency. And here we say that a relation should have at least three attributes. Then only it makes some problem for us. Otherwise, it is easy to solve this problem if we have only two attributes. And for a relation with attributes A, B, C, and we can say A multi determines B, that is a multi-value dependency, and if B and C are independent of each other. So we have three attributes like A, B, C, and we are defining a multi-value dependency for this A and B. A determines B, and we can say that B and C are independent of each other. Then only this multi-value dependency makes sense. Okay, so A multi determines B, but there is no connection between B and C. B cannot determine C, or C cannot determine B. And these are we can summarize that like this. These are the conditions for multi-value dependency, that is A to B, that is multi determines B for a single value of A more than one value for B exists. Okay, and a relation should have at least three attributes, and for this relation with attributes A, B, C, we can say B and C are independent of each other. Okay, and again this 4NF actually eliminates independent many to one relationships between attributes. Okay, so what is many to one relationships? Independent many to one relationships between attributes will be eliminated in the case of 4NF. Okay. And this is a formal definition for this multi-value dependencies. So that is a definition. A multi-value dependency, you can call it as MVD, that is X multi-determines Y specified on relation schema R, where X and Y are both subsets of this R. Okay, it is subsets of this R, and that specifies the following constraint on any relation state R of capital R. Okay. So these are the constraints. If two tuples T1 and T2 exist in R such that T1 of X equal to T2 of X. Okay, two tuples of the same values for this X. Then two tuples, you can again define two more tuples, that is two tuples T3 and T4 should also exist in R with the following properties, where we can use this Z to denote R minus X union Y. Okay, and the conditions are T3 of X equal to T4 X, which is equal to T1 of X equal to T2 of X. Okay, so these four values are same. Or you can think it like this, for the other side, that is Y, T3 of Y is equal to T1 of Y. Okay, and T4 of Y is equal to T2 of Y. Okay, or you can have T3 of Z equal to T2 of Z and T4 of Z equal to T1 of Z, where Z is nothing but you have this R and you take this X and Y, take their union, those attributes will be removed from this schema, and still you have a relation that you can call it as Z, and when you take the Z for T3 and T2, tuples T2 and T3, their values will be same, and for T4 and T1, their values will be same. Okay, that is just reverse of this. Okay, so an MVD, that is a multi-value dependency X to Y in R, is called a trivial MVD if Y is a subset of X. Okay, suppose Y is a subset of X, then it is trivial. Or X union Y is equal to R. Okay, if these two conditions hold, either this, that is Y is a subset of X, Y is a subset of X, then this multi-value dependency is trivial. Or if X union Y equal to R, and in that case also it is trivial. And these are some inference rules for functional and multi-value dependencies. Okay, so we have seen some examples earlier in some other scenario. So that is first inference rule, that is reflexive rule for FDs, that we have already seen. If X is a subset of Y, then X determines Y. And augmentation rule, that is IR2 for functional dependencies again, that is if X to Y, then we can say XZ to YZ. Okay. Then we have transitive rule for FDs, that is X to Y, Y to Z, then X to Z. Then we have IR4, that is complementation rule for MVDs. Okay. That is X to Y, that means X to R minus X union Y. Okay, so that is an inference rule. X to Y. Suppose X multi-determines Y, then it says that X multi-determines R minus X union Y. And fifth one is augmentation rule for MVDs. That is, if X multi-determines Y and W is a subset of Z, then WX determines YZ, just like IR2. And we have IR6, that is again transitive rule, X to Y and Y to Z, which means we have X to Z minus Y. And IR7, that is a replication rule for FDs to MVD, that is X to Y means X multi-determines Y. Okay. And IR8 is coalescence rule for FDs and MVDs, that is if X determines Y, and there exists W with the property that the property is W intersection Y is empty and W determines Z and Y is a subset of Z. In that case, you can say X determines Y. Okay. X multi-determines Y and X determines Z when these conditions are true. That is, we can define another W and W intersection Y is empty. You have this Y and W determines Z and Y is a subset of Z. Okay. And in that case, you can say X determines Z. And we can have a formal definition for a fourth normal form, that is a relation schema R is in 4NF with respect to a set of dependencies F. Okay, that includes functional dependencies and multi-value dependencies. So here we are talking about functional as well as multi-value dependencies. So F means a set of functional and multi-value dependencies. If for every non-trivial multi-value dependency, we are talking about non-trivial multi-value dependency only here, and X determines Y in F closure. Okay, so this is a non-trivial multi-value dependency, that is X determines, multi-determines Y, that is in F closure, then X is a super key for R. Okay, if we have X multi-determines Y and that kind of a dependency is there in F closure, then we can say that X is a super key for R. And we know what is meant by F closure. That is the complete set of all dependencies. Okay, here it is functional or multi-value dependencies that will hold in every relation state R of capital R that satisfies F. And it is known as a closure. And consider an example here. We have an employee relation and there we have two multi-value dependencies, that is we have employee name Smith, P name, D name. Okay, employee name, project name and department name. So here for the same employee Smith, one employee can work for different departments or different projects, and one employee can have multiple dependents. Okay, so Smith working for X, project X, and with dependent name John. Okay, and again Smith for Y with Anna, and Smith with X for Anna, and Smith Y for John. Okay, so for the same value you have multiple values here. Okay, that is multi-value dependency. So here the multi-value dependency, there are two multi-value dependencies, E name to P name. E name to P name, Smith to X and Smith to Y. That is one multi-value dependency. And another multi-value dependency is between E name and D name. E name, that is again with Smith to John and Smith to Anna. So we should eliminate this multi-value dependency. So for that, again the algorithm is to decompose the employee relation into two 4NF relations, employee underscore projects and employee underscore dependents. Okay, so we have employee underscore projects and employee underscore dependents. So here employee name, employee underscore projects means employee name and project name. Employee underscore dependents means employee name and dependent name. So here it is Smith X, Smith Y. Okay, that is enough. Instead of this 4 entries, we can have only 2 entries here. And for dependents, again we have 2 dependents for Smith, Smith John and Smith Anna. Okay, so now we have two relations from this employee relation, and there it is now in fourth normal form because we have eliminated this multi-value dependency, and we can say that if we have only two attributes in that relation, then we don't think about this multi-value dependency. And again, one more condition is there. We have at least 3 attributes, and this employee name depends on this project. And when you think about this P name and D name, these two are independent. Okay, and P name and D name are independent of each other. Okay, this is for this is another example. So that is we have the same example with more data. Smith, Brown and Brown. So we have again dividing this into employee underscore projects and employee underscore dependents. So there we have E name, P name. So Smith with P name X, Smith with P name Y, and Brown with W, X, Y, and Z. Okay, only 6 entries here. And employee underscore dependents. There again, Smith has 2 dependents, Anna and John. Brown has Jim, Joanne, and Bob. Okay, so 3 dependents. So we have 6 plus 5 entries altogether. Okay, so here 16 entries here. Okay, so that is reduced to 11 entries. So and they both are in 4NF. And we can satisfy this lossless non-additive joint decomposition property. Okay, lossless joint property. So it is a lossless non-additive joint decomposition into 4NF relations. Okay, so that is a property, lossless joint property, property LJ1. So the relation schema R1 and R2 form a lossless non-additive joint decomposition of R with respect to a set F of functional and multivalue dependencies if and only if there are 2 conditions, that is one condition R1 intersection R2 that determines R1 minus R2, and by symmetry we can write it as R1 intersection R2 multi determines R2 minus R1. Okay, if this condition holds, then we can say it is a lossless joint decomposition. Okay, so when you take R1, that is into 2 sets schemas R1 and R2. So when you take R1 intersection R2, that is nothing but R1 minus R2. Okay, or R2 minus R1. Then there is an algorithm, and that is for relational decomposition into 4NF relations with non-additive joint property. So again we have an input, that is a universal relation R and a set of functional and multivalue dependencies F. So initially set D as the given universal relation R. And while there is a relation schema Q in capital D that is not in 4NF, if we get a relation schema from this D which is not in 4NF, then we can do this step. Choose a relation schema Q in D that is not in 4NF. Find a non-trivial MVD X to Y in Q that violates 4NF. Okay, so you just find out one non-trivial MVD and replace this Q in D by 2 relation schemas Q minus Y and X union Y. So our aim is to remove this multi-value dependencies. That is, we get that is we should get a decomposition which is in 4NF with non-additive joint property. That will be satisfied if we get 2 relation schemas Q minus Y and X union Y. Okay, so we replace this Q violates this 4NF, and that will be decomposed into Q minus Y. We just remove this Y from here, and the second thing will be X union Y. That is according to the definition. So let's move on to the joint dependencies and fifth normal form. So what is meant by a joint dependency? A joint dependency, you can call it as JD, and that is denoted by JD of R1, R2, etc. Rn specified on a relation schema R that specifies a constraint on the states R of capital R, and the constraint states that every legal state R of capital R should have a non-additive joint decomposition into R1, R2, etc., Rn. That is, for every such R, we have this star pi R1 of R, pi R2 of R, etc., pi Rn of R should give you the same R. Okay, so we are decomposing this relation R into R1, R2, etc., Rn. Okay, so what we mean is that we'll be able to, given a relation schema R, we'll be able to decompose that into R1, R2, etc., Rn. And when we join this R1, R2, etc., Rn together, we should get this R back. Okay, that is known as a joint dependency. So, and MVD is special case of a joint dependency where n is equal to 2. Okay, so when n is equal to 2, that is, this joint dependency is known as a multi-value dependency. That is, we are decomposing that into two relations only in the case of a multi-value dependency. But in the case of a joint dependency, we will be able to decompose that into n. Okay, n relation schemas. Okay. So a joint dependency JD of R1, R2, etc. Rn specified in relation schema R is trivial JD if one of the relation schemas Ri in JD of R1, etc. Rn is equal to capital R. Okay, that is what it says. It is trivial means one of the relations, that is one of the relation schemas Ri in this thing is equal to capital Ri, and I mean R, then it is a trivial JD. Okay. And now we can define a relation that is a fifth normal form. So a relation schema R is in fifth normal form, that is 5NF. We can call it as a project join normal form with respect to a set F of functional, multivalued and joint dependencies if for every non-trivial joint dependency JD of R1, R2, etc. Rn in F closure that is implied by F, then every Ri is a super key of R. Okay, that is the condition. Every Ri is a super key of R. So when you have a joint dependency like R1, R2, etc., Rn, then every Ri is a super key of R. That is known as a fifth normal form. Okay. So here we can consider the example of a relation, supply relation. We have seen it earlier. The main peculiarity is that the supply relation is a all key relation, which means all attributes are keys. And suppose that we have an additional constraint here, that is whenever a supplier, and I told you this before, whenever we have a supplier S which supplies a part P, and for a project J suppose uses this part P and the supplier S supplies at least one part to project J. Okay, if supplier supplies at least one part to project J, then supplier S will also be supplying part P to project J. Then this constraint can be restated using this kind of a joint dependency, and that is JD of R1, R2, R3. Among the three projections, we have R1 here, that is S name, comma part name, and we have R2, that is S name, comma project name, and we have R3, that is with part name, comma project name of supply. Okay, so here the main problem is that this is with no multivariate dependencies. That's why it is in 4NF, but it is not in 5NF, because we can again decompose this into relations like R1, R2, R3. Okay, and when we decompose this into these three sets, we can define a joint dependency. It means that when we perform a join operation on this, we'll be able to get back this supply. Okay, and that is from R1, and our constraint is that we'll be able to decompose this supply into R1 S name, comma part name, R2 S name, comma project name, R3 part name, comma project name. And if this constraint holds, the tuples in this relations must exist in legal state of the supply relation. Okay, and we can say that this supply relation with the joint dependency is decomposed into three relations R1, R2 and R3, and these each are in 5NF. And when we apply a natural join to any of these two relations, what will happen? We can say that if you apply this natural join to any of these two relations, we'll get spurious tuples. But when we perform a natural join on these three relations, we'll get the original, that is the supply relation. Okay, so the point is, when we perform a natural join on any two relations, then it will lead to spurious results or spurious tuples. But when we apply a natural join to any, to all three together, then we'll get R back. Okay, so that is about this fifth normal form. So we have this supply relation, and that is not in 5NF. It has a joint dependency R1, R2, R3, and we can divide R1, R2, R3, and it is with these attributes. Okay, so if we can decompose this like this, then this is in, these three are in 5NF. And again we can say, when we perform a natural join on these three relations together, we'll get back the original R. Okay, that's all about this 4NF and 5NF. Thank you.